Howdy, all. Welcome to Chapter 7, Unit 7. Here we go. So, we are going to talk about sampling distribution, something that you did talk about in Algebra 2, so this will not be an entirely new concept to you. We will dig a little deeper, though. So, in this section 7.1, this video, we're going to talk about what the difference between a parameter and a statistic are, and then how we can use a sampling distribution to evaluate a claim. We're going to talk about if a claim or if a statistic is biased, unbiased, and then look at the relationship between sample size and variability, which we already know quite a bit of, actually. So, in this first part, parameter and statistic, I want you to think about P for parameter and P for population. Population parameter. A parameter is some number that describes a characteristic of the population. It might be the median income of everyone in Henrietta. That would be the population parameter. And the sample statistic would be the sample median income for my sample of people in Henrietta. So population parameter, PP, sample statistic, SS. All right. So in reality, we're going to know the sample statistics and try to evaluate claims about the population parameters. In this chapter, though, it's going to be a little bit different. Just to set the foundation, we're going to know the population parameter and then see if what happened in the sample is unusual or unlikely. Okay. So this is just going through that specific thing. As far as the population parameter and the sample statistic, there are symbols that go along with them, and we will get to those. So check your understanding. Go ahead, read through this, pause the video, come on back when you're done, and we'll take a look at how you did. So in this scenario, that the Arizona iced tea bottles were supposed to contain an average of 20 ounces of iced tea. So that's an average. That's from all of the bottles. That's a population parameter. And the correct notation would be mu. That's the population mean. We try to estimate that by taking a sample mean. And that's the 19.6. That's the sample statistic, which is the sample mean in this case. And that would be denoted by X bar, which is the sample mean. There they are. Okay, for number 2, we are talking about 8% of the 125 passengers were selected. Well, that's a sample. So that is a sample statistic. Now we're talking about a proportion. So we call that the sample proportion, or P hat is 0.08. And this 10% is all passengers. So this would be the population proportion, which we call P. So this is the population parameter, P, and the sample statistic, P hat. All right, moving along. Sampling variability. Well, this is the idea that a value for a statistic, it's going to vary when we take a random sample. So let me give you an example. If we're trying to estimate what percent of the population has brown eyes, and we randomly sample 100 people, we might find out it's 48%. And then we do another random sample of 100 people, it might be 46%. And another one might be 53%. There's going to be some variability in the sampling. But over and over, that's going to start to follow a pattern, and we can use that information to then make conclusions. So that's what they're doing here. They're looking at what percent of these chips end up being, I think it's red. So you can see in this one sample, 20% of the chips were red, 30%, 35%, 40%, and so on and so forth. So then we can get into discussing the center, the shape, the variability as we've done in the past. That's nothing new. And eventually we're going to calculate the mean and the standard deviation. So the sampling distribution of a statistic, so whether it's the sample mean, the sample median, the sample IQR, it can be anything, is just all the possible values that the sample could take on if we took every single sample possible of that size. All right, so let's take a look here. Okay, this idea is really important, and I'm going to try to highlight what this is trying to say. So in this scenario, they had half the chips were blue, half the chips were red. This is the population distribution. Then we take a random sample. We take a random sample of 20 chips. In one of the samples, 60% were red. I'm sorry, 60% were blue, 40% were red. Math is hard right now. In another sample, we have 45% blue, 55% red. This is that sampling variability. So this is a graph of the sample distribution. Notice I said sample, one sample. Now, if I take the sample proportion, the proportion of the red chips, 40%, put it into a dot plot, 55%, put it into a dot plot, and do this for every single sample of size 20 from the population, I would have the sampling distribution. All the possible values I could get for the proportion of red. And then I can start to see a pattern. I can describe the center, the shape, the variability, and see what values are unusual, which ones are not. Is it statistically significant? Is it not? Okay, let's do the same thing we always do. We're going to run through this check of understanding. Go ahead, pause the video, work through this, and come back and join me going through it. All right, so in this scenario, we have M&Ms, and we have the 6 different colors of M&Ms. And the company claims blue is 24%, orange 20, green 16, yellow 14, red and brown 13. So they want to examine the proportion of orange M&Ms in repeated samples of 50 candies. Graph the population distribution and identify the individuals, the variable, and the parameter of interest. Individuals are the M&Ms, the variable is the color, and the parameter of interest is the proportion of orange M&Ms. So this would just be literally graphing the 6 different colors, which you can see here. It's a categorical variable, hence the bar graph. Okay. For question 2, imagine taking a simple random sample of 50 M&Ms. Make a graph showing the possible distribution. Possible. So I might get, I don't know, I might get 5 orange M&Ms. 5 out of 50 is 10%. So that would be my sample statistic, that 10%. Okay, this is just a possible one. So they're looking at the frequency instead of the probability. So these would add up to 50 for orange. They have 11 out of the 50 or 22%. That's a sample distribution. We took one sample. Which of the following graphs could be the approximate sampling distribution? Okay, the first one is absolutely out without a doubt. This is a bar graph. It's not graphing the sample proportion over and over and over and over. Sampling, I'm doing it over and over and over and over again. So as I look at the second and the third one, these are both graphing the sampling distribution. Okay, if we know that, what did they say? The claim is 13%, orange, 20% are orange. Then on average, 20% of the candy should be orange more often than anything else. So if I look at graph 2 and 3 here, graph 2 is centered at 20%, graph 3 is centered at 40%. So this middle graph would be the correct choice of an approximate sampling distribution. And they just talk about the fact it should be centered at that point too. And that's why it's that middle choice and not the one on the right. All right. So then we get into describing the sampling distributions. And we talk about the center. Is it biased or unbiased? And if you remember way back when we did the Beyonce activity and we looked at what was the average word length when you just picked and when you did a random sample. When we just picked a convenient sample, we consistently overestimated. So say the average word length was 3.5 and we kept getting means above 3.5. We were overestimating. Unbiased means we should have some overestimating, some underestimating, but the distribution should be centered at the true value. So here, it's unbiased if the mean of the sampling distribution is equal to the mean of the parameter. So the mean of the sampling distribution has to equal the population mean. If that's the case, it's unbiased. If not, then we have a bias. So here, 50% of the chips were red. This sampling distribution is centered at 0.5. This would be unbiased. Okay. don't like those examples that well. Okay. Then we get into variability. Lower variability is better. We want to have answers that are precise as possible. And the higher the sample size, the less variability we're going to have. We're going to have more precise data, more precise estimates. So in this case, sample size of 100, sample size of 1,000. They're both centered at about, looks like 36, 37%, the true value. So they're both unbiased. But the sample size of 1,000 is a lot more precise. So that would be a much better indicator for the true value. All right. Okay. All right. Let's do the same thing with the check of understanding. Go ahead, pause the video, work through it on your own, and then come back. I'll scroll down so you can see the whole thing, most of it. So for the first question here, is the sample mean sample median. It's not always mean. Sample median unbiased to the population median. So they got to give us some information. All right, the median for the population is 75. So then the sampling distribution should be centered at 75, but it's not. It's centered at 73.5. So is this an unbiased? No, it's a biased estimator. It looks like we're consistently underestimating the true median. Okay, they're not equal. It's literally black and white there. Number two, if we did samples of size 20 instead of 10, the variability or the spread would be smaller, more precise, because we're sampling a larger part of the population. Larger samples, more precise estimates. Larger samples include more information about the population. Better said than I did. All right, describe the shape of the sampling distribution. So here, if I were to draw a curve over this, to me, this looks skewed to the left and unimodal. That would be the shape of the sampling distribution. There you go. So let's talk about a couple of things. We have bias, variability, and shape. So if we think about like a dartboard here, high bias means we're not aiming in the right place. It's not centered at the right value. Low variability, we're very precise, but we're consistently missing the mark in the same spot. Low bias, we have some under and over estimates, but on average, we're hitting the mark. High variability, we're just kind of all over the place. High bias, high variability. High bias, we're consistently over or underestimating, so we're not hitting the mark, and we're all over the place. Ideally, we have no bias or low bias. We're hitting the mark consistently and low variability. So that comes from having a random sample and a large sample size. If you're interested in history, this German tank problem is awesome. It goes through in World War II how we were able to figure out how many tanks the Germans had just based on the numbers on the tanks without being able to see them all. It's a pretty cool application of this. All right. Next. All right, so summary. When we take a sample, hey, there's the bell. We calculate a statistic. It's a numerical value from the sample. It could be a quartile, it could be a median, it could be a mean, some specific piece of data that we're trying to estimate from the population. What we're trying to estimate in the population is what we're calculating. So if I want the population mean, I estimate it with the sample mean. If I want the population standard deviation, I estimate it with the sample standard deviation. So the numerical part is the same thing. One is from a population, that's the parameter. One is from a sample, it's the statistic. Make sure you're clear on a population distribution. Think of the M&M question. It's the graph of all the colors and what percent likelihood that they occur. The sample or the distribution of the sample data, we take one sample of 50 M&Ms and we graph their colors. The sampling distribution has nothing to do with graphing colors. I'm graphing a statistic. In this case, I was graphing the percent of orange M&Ms over and over and over and over again from repeated sampling. Unbiased estimator means your sampling distribution is centered at the parameter. Biased means it's not. Variability is all due to the sampling size. Larger sample size, less variability, more precise. And ideally, we want unbiased, low variability is ideal. So that was the video on section 7.1. I hope you enjoyed it. And here's my face. Maybe that made it a little more exciting, or maybe you didn't want to see that at all, but too bad. Here I am. Have a nice day.